Okay, this is part 2 of the instrumentation amplifier. So now we'll be considering the applications of the instrumentation amplifier, different applications. So first is the temperature indicator. So the same circuit, whatever we have used for 6.12, which is the figure over here, can be used for the temperature indicator if the transducer in the grid circuit is a thermistor. If the transducer in the grid circuit is a thermistor, which is there over here, this is a thermistor, then it becomes the temperature indicator. And the output meter is calibrated in the degree Celsius or Fahrenheit. The grids can be balanced at the desired reference condition. For instance, at 25 degrees centigrade, we can assume that the grid is balanced. And as the temperature varies, if it goes less, reduces or increases, then the resistance of the thermistor changes and the bridge becomes unbalanced. This unbalanced bridge in turn produces the meter movement. The meter can be calibrated to reach the desired temperature range by selecting an appropriate gain for the differential instrumentation amplifier, which is RF by R1. So in the figure, the meter movement is dependent on the amount of imbalance in the circuit, and that is the change in the del R in the value of the thermistor resistance will change the, will change the meter movement. So the del R for the thermistor, however, can be generally written like this. That is, del R is equal to temperature coefficient of resistance multiplied by final temperature minus the reference temperature. Temperature coefficient of resistance multiplied by final temperature minus reference temperature. So reference temperature will be 25 degrees. Final temperature is what we have, either might be 45 degrees or might be 15 degrees or whatever. Then here we have the temperature coefficient of resistance, that is how much resistance is changing per degree centigrade. So let us take an example. In the circuit of figure 6.12, R1 equal to 1 kilo ohm, RF equal to 4.7, that is the instrumentation amplifier is having RF by R1 equal to 4.7 by 1 kilo ohm. RA, RB, RC are same, that is equal to 100 kilo ohm. VDC is plus 5 volts. Op-amp supply voltage is plus or minus 15 volts. This transducer is a thermistor with the following specifications, that is RT is equal to 100 kilo ohms at reference temperature, same as RA, RB, RC, that is 25 degrees centigrade. Temperature coefficient of resistance is minus 1 kilo ohm per degree centigrade. So resistance will be changing with minus 1 kilo ohm per degree centigrade. It's a negative temperature coefficient there, or 1% per degree centigrade. So 100 kilo ohm minus 1 kilo ohm. So 1% per degree centigrade. Determine the output voltage at 0 and 100 degrees centigrade. So we need to find first del R. So del R will be is given minus 1 kilo ohm per degree centigrade as the temperature coefficient. Multiplied by final temperature is 0 degrees in the case 1, 0 minus 25, and that will give us 25 kilo ohms. Now going back to the formula for V naught, this is V naught. So V naught is RA by R1 into del R by 4R into VDC. So RF by R1 is 4.7 by 1 kilo ohms multiplied by the value of the 25 kilo ohms value del R over here divided by 4 into R. 4 multiplied by 100 kilo ohms multiplied by the value of VDC, which is 5 volts. So you'll get 1.47. Similarly, if the temperature changes to 100 degrees, then del R will be minus 1 kilo ohm divided by minus 1 kilo ohm per degree centigrade multiplied by 100 degrees centigrade minus 25 degrees centigrade, that will be minus 75 kilo ohms. So only change will be minus 75 kilo ohms. All other things are same. Okay, all other things are same. So we'll get V naught is equal to minus 4.41 volts. So thus, when V naught is equal to 1.47 volt, the meter phase can be marked as 0 degrees centigrade, and when V naught is equal to minus 4.41 volts, the meter phase can be marked as 100 degrees centigrade. Also, when we have 25 degrees centigrade, V naught is equal to 0. Therefore, a center zerometer is used, thus using the resistant temperature characteristic of a thermistor. The meter can be calibrated from 0 to 100 degrees centigrade. Thermistors which are having relatively high resistance, RT much greater than 1 megohm, and sensitivity also very large, temperature coefficient of the resistance which is greater than 3% per degree centigrade, are most suited for the remote measurement, because the temperature effect of transmission line resistance will be negligible when we choose the value of RT to be 1 megohm. Next, we come to the temperature controller. The next application is a simple, inexpensive temperature control circuit may be constructed by using a thermistor in the bridge circuit and by replacing the meter with a relay in the circuit of 6.12. So we had a meter there. In place of meter over here, we can just put a relay. The output of the differential instrumentation amplifier drives a relay that controls the current in the heat generating circuit. A properly designed circuit should energize a relay when the temperature of the thermistor drops below a desired value. So if the temperature of a thermistor drops below a desired value, the relay is energized, causing the heat unit to turn on, so that again the temperature will go on increasing. Next application is light intensity meter. So in the circuit, again figure 6.12, we can use the light intensity meter if the transducer is a photocell. So you use transducer as a photocell, and the light intensity meter can be used. The bridge can be balanced for darkness conditions. So when we use the transducer as a photocell, then the whole device will act as a light intensity meter. The bridge can be balanced for darkness conditions. Therefore, when exposed to light, the bridge will be unbalanced and cause the meter to deflect. The meter can be calibrated in terms of lux to measure the change in light intensity. The light intensity meter using an instrumentation bridge amplifier is more accurate and stable than single input inverting and non-inverting configuration, because the common mode voltages are effectively rejected by the differential configuration. CMRR value is much larger for the differential configuration than for an inverting and non-inverting amplifier. Now let us come to the next application, measurement of the flow or the thermal conductivity. So a flow meter or a thermal conductivity meter may be constructed using the circuit again of 6.12, provided that two thermistors are used adjacent to each other. For example, we might use RC and RT as two thermal, RT and RC. This is RT and this is RC, can be what you call thermistors. Two identical thermistors. For the flow measurement, one thermistor is sealed in a small cavity copper cylinder and the other installed in a small copper pipe. So when we make the air to flow through the pipe, the bridge can be balanced. When no air flows through the pipe, the bridge will be balanced. No air flows through the small copper pipe over here, then the bridge is balanced, so that output voltage is 0. When we make the air flow over the thermistor in the small copper pipe, its temperature decreases and in turn the resistance increases, causing the bridge to be unbalanced. This unbalanced voltage is then amplified by the differential instrumentation amplifier and applied to the meter. Thus, the amount of meter deflection is proportional to the flow rate of the air in the pipe. The meter can be calibrated in meters per second to accommodate the desired flow range rate. For thermal conductive measurement, two thermistors are mounted in separate copper cylinders. With air in both cylinders, the bridge can be balanced and hence output will be zero. When air in one cylinder is replaced by a medium being tested, for example, say a carbon dioxide, then the you can measure the thermal conductivity of the air and the thermal conductivity of the gas which is sent will be different. Because of that, the bridge will be imbalanced, and hence we will get to measure the thermal conductivity. So this happens because the temperature of the thermistor changes and thus changing its resistance. Suppose that the medium being tested is carbon dioxide. Because of its lower thermal conductivity, CO2 will increase the temperature of the thermistor, which will cause a decrease in the thermistor resistance. This results in the unbalancing the bridge, which in turn produces a meter deflection. So we can calibrate the meter in terms of the relative thermal conductivity, which is given over here. Then we come to the next application, which is analog weight scale. By connecting a strain gauge in the bridge, the circuit of the figure can be converted into a simple and inexpensive analog weight scale. So in the analog weight scale, strain gauge elements are connected in all four arms of the bridge. The elements are mounted on the base of the weight platform, so that when an external force or weight is applied to the platform, one pair of the elements in the opposite arms elongate, whereas the other pair of elements in the opposite arms compress. So that just means that when the weight is placed on the platform, RT1 and RT3 both decrease in the resistance, RT2 and RT4 both increase in resistance, or vice versa. So when no weight is placed on the platform, the bridge is balanced. That is, RT1 equal to RT2 is equal to RT3 is equal to RT4 equal to R. And the output voltage of the weight scale can be zero. When the weight is placed on the scale platform, the bridge becomes unbalanced, assuming that RT1 and RT3 decrease in resistance and RT2 and RT4 increase in resistance by the same number of ohms del R. The balanced bridge VAB is given by VDC into del R by R. VAB is equal to minus VDC by del R by R. So where VDC is the DC excitation voltage, and RT1, all the strain gauge resistances RT1 to R4 will be equal to R, and del R will be the change in the gauge resistance when a weight is put. So if the decrease in gauge resistance R1 and RT3 is del R, and the increase in resistance RT2 and RT4 is again del R. Therefore, with this assumption, the voltage VA is less than VB and the output voltage VAB is negative, as indicated in the equation which is written over here. The voltage VAB is then amplified by the differential instrumentation amplifier, which derives the meter. Since the gain of the amplifier is minus RF by R1, the output voltage V0 will be equal to V0 equal to VDC into del R by R. That means this quantity is to be amplified. Multiplied by minus RF into R1 will give you this quantity. So this minus and the minus RF, minus of the RF by R1 will cancel, so we'll get a positive voltage. So the gain of the amplifier can be selected according to the sensitivity of the strain gauge and full scale deflection requirements of the meter. The meter can be calibrated in terms of kilograms. So for better accuracy conditions, the microprocessor-based digital weight scale may be constructed. However, such a scale is much more complex and expensive than the analog scale. Now let us take an example here. Again, the circuit we are taking 6.12 only, where we use all the 4 arms to be the strain gauge. The gain of the differential amplifier, differential instrumentation amplifier is minus 100. That means RF by R1 will be plus 100. And the VDC value is 10 volts. Then the op-amp supply voltage is 10 volts. And the unstrained resistance of each of the 4 elements is 100 ohms. And when a certain weight is placed on the scale system, the output voltage will be the value equal to 1 volt. Assuming that the output is initially 0, determine the change in the resistance of each strain gauge element. So using this equation which we have written over here, V0 is equal to VDC into del R by R into RF by R1. We can just write RF by R1 is 100 given to us, VDC is given as the value 10 volts, and del R is given to us as the output voltage is given as 1 volt, and the value of the resistor is also given as 100 ohms over here. So all that is substituted over here. So 1 is equal to 10 del R by 100 to 100. So del R will be 0.1 ohms. This means that RT1 and RT3 will decrease by 0.1 ohms if RT2 and RT4 increases by 0.1 ohm when the certain weight is placed on the same platform. Thank you. With this, we come to the end of the instrumentation amplifier. Thank you.